Hey, you're back. Bill Witte, the Math Twitty here, back with more algebra for you. Today we're going to cover roots. Now, roots are going to be of great use to us when we go and try and solve exponential equations, etc. Okay, next time. But today we're going to do the basics of roots. Now, they're also called radicals. Okay, now this isn't the Jane Fonda type of radicals we're talking about here. These are going to be numeric radicals. I guess you can see with roots and radicals where that sign came from. It looks a lot like an R, doesn't it? Okay, well, let's dig in. Don't forget that if you have any trouble or if you need to review what we talk about today, or if I talk too fast, which happens, you can always go to www.montgomerycollege.edu/algebra on the web. Okay? So let's get back to and dig in with our root basics. Before we do root basics, I think it's going to behoove us to review things pertinent to that. Actually, the inverse of roots and radicals would be exponents. So let's do it backwards first, and then it'll be easy. Okay? Remember that multiplication, this is very basic, 5 times 3 really means 5 plus 5 plus 5, right? That's the basics. You can see where the 3 goes to when we're talking about multiplication. It's really multiple addition, hence the 15. But when we talk about exponents, 5 not times 3, but 5 to the 3, or to the third power, now we still have 3 5s, but they're not added. Remember that they're multiplied. That's what the exponents mean. And we're going to kind of do that backwards with roots. In this case, we don't get 15, but rather 5 times 5 times 5. We get 125. Let's take an example of this other than 5. For instance, 2 to the 4th power, there's going to be 4 2's, right? 2 times 2 times 2 times 2, 4 times. What is that? 16, isn't it? What about 2x to the 5th? Now that 5 next to the x to the 5th by the order of operations only has power over the x, not the 2, does it? So we're only going to have 5 x's. You know, remember the order of operations tells us to do our exponentiation first, then the multiplication between the 2 and the x. Hence, we only have 5 x's. Okay? As you can see. Now, if we change that just a little bit and put the 5 outside of parentheses, now the 5 has power over the 2 and the x, because the order of operations tells me, first of all, to do what's in parentheses first. Okay? So in this case, completely changes the answer. We're going to have 5 2's and 5 x's. Okay, just a little review. Something like this, 3 to the 2th times 3 to the 4th. As you can see, we're going to have 2 3's multiplied and 4 3's multiplied. It's going to end up being some high number, 3 to the 6th. You may start to remember some of the rules of exponents. We're not going to get into that today, but that's as far as we need to talk about exponents. Okay? Now, let's see. We're ready for root basics. This is called, you see the R? This is called the root, or in this case, the square root, we'll do others, the square root of 25. What is the square root of 25? Is it 5? Well, it is, because 5 to the 2th, hence the term square, 5 squared ends up being 25. So the square root of 25 is 5 for that reason, because if we square it, we get, I like to say the square root, R-O-U-T-E, the way to get 25 by squaring a number would be 5. How about the square root of 16? I'm betting you can predict what that is. Is it 4? Well, that's the beauty of these problems. You can always prove it by squaring it and testing out. 4 squared, 4 times 4, son of a gun, it does equal 16, so it is the square root of 16. It is a square root of 16, I should say. There may be another. The square root of 81, think about that. What would that be? Some number, when you square it, you get 81. Let's prove it. 9 to the 2th, or 9 squared, does equal 81. So 9 is, in fact, the square root, or a square root, of 81. Now, it's going to be useful for us to get to know, don't say memorize, yes, memorize, some of the perfect squares and square roots. Okay, we're going to be using this all throughout the class today. If I square root 4, we get 2, because 2 squared is 4. What's the square root of 9? 3. Get to know these. The square root of 16. These are the easier ones, if you would. They get higher. The square root of 25. The square root of 36. Do you know your multiplication tables? We're getting higher. The square root of 49. Square root of 64. And they go higher, and the higher you can remember, the easier life's going to be as we go on. I'm not going to go any higher than that, but you get the idea. It's going to help you to know your multiplication tables. Now, we can play the same game with, it's going to get a little bit harder, with variables. Okay? We take a square and a square root. The square root of x to the 2th, think about it, the number that you have to multiply by itself to get x to the 2th, the square root of x to the 2th, is x. Of course it is. Okay? What about the number that you have to multiply by itself to get x to the 4th? X to the 2th. Yes, x to the 2th times x to the 2th does equal x to the 4th. Now, here's where it gets difficult. What number times itself equals x to the 6th? The square root of x to the 6th, might surprise you a little bit, is x to the 3rd. Remember the rules of exponents, that we add exponents. So x to the 3rd times x to the 3rd does in fact equal x to the 6th. X to the 8th, that is a perfect square. We can take the square root and we get x to the 4th, because x to the 4th times x to the 4th does equal x to the 8th. Now I'm noticing that it looks like all the even exponents have a perfect square root. The square root of x to the 10th would be x to the 5th, because x to the 5th times itself does in fact equal x to the 10th. Leads then that the square root of x to the 12th, of course, is x to the 6th. As you can see the pattern here. Get the idea? Here's all your square roots, and I want you to memorize them, and I'm not kidding. It's going to be of use to you. Okay? Okay, now, the square root. Now, what about the non-exact square roots? This wasn't in the list. The square root of 14. What is that going to be? Some people say, oh, there's no such thing. It doesn't exist. Oh, it does.
There must be some way. There just gotta be. I've got it.
Well, we know one thing for sure. We know the square root of 9, and it follows that the square root of 14 is more than the square root of 9, because 14 is bigger than 9. And the square root of 9 is what? 3. Okay, do I know any other square roots that are bigger than the square root of 14? How about the square root of 16? Okay, and that was one that we asked you to kind of memorize, get to know. The square root of 16 is 4. So it leads to follow that the square root of 14 is somewhere between 3 and 4. Okay? And I'm guessing that it's a little bit closer to 4, since 14 is closer to 16 than it is to 9. Well, you know what? The square root of 14 is about 3.74. I say that it's about 3.74. It's a little bit more than 3.74, and I'm going to demonstrate that for you in a second. But the point is, if I multiply 3.74 by itself, 3.74 squared, or 3.74 times 3.74, I'm going to get a number very close to 14. Okay?
There's something squirrely around here.
Well, that's a problem. This is not going to be exact in this case, but it's close to being the exact square root. Okay? square root of 14 doesn't come out exactly as I say. Many of them don't. Most don't. What about the square root of 8? Well, anything that we know that's close to the square root of 8. The square root of 4 is smaller than the square root of 8, that's for sure, because 4 is smaller than 8. So this square root of 8 is bigger than 2. And it's less than, the square root of 8 is less than the square root of 9, which is what? 3. So I'm guessing that this number is somewhere between 2 and 3. The number that you square and get 8 is somewhere between 2 and 3, probably closer to 3 because 8 is closer to 9. Okay, well guess what? The square root of 8 doesn't come out exact, is about equal to 2.83. I've rounded it to the hundredth, okay? But actually it goes on and on and on as far as decimals. If I take 2.83 and square it, now this time it's going to be a little bit too big, isn't it? 2.83 times 2.83. So it's probably 2.82, some 2.82198762 kind of a thing. These decimals that are not exact go on and on and on. So it's close, and that's what we'll use. Now we can do this with a calculator. We can take square roots. The buttons that you should know to use to do square roots on a calculator are, of course, the on button. Now this is the x squared button. Okay, now we're not doing a square, but we're doing the inverse of that, the square root. If we do second and then x squared, you'll see the little square root above that x squared button. It will take the square root of that number. So we have to use second and x squared to do that. Okay? And after we've put that in, we're going to actually hit enter to tell it to give us the answer. So basically, we'll be hitting in this order to take the square root of a number. The little button that says second, x squared button. Okay, it's not the x button, but the x squared button. Then we'll type the number, and then we'll hit enter. Okay, now let's try it. Okay, let's go over here and actually try it. I'm going to try and take the square root of my number, the first one, 14. So let me turn this baby on. Okay, I'll clear out what I got. And I'm going to do the square root. So I'm going to do second, and then x squared. And you see the little square root sign, the little r, the radical sign. And I'm going to type in a 14, and then hit enter. I have to hit enter to tell it that I've done the number. And I get, as I told you, it's not exact, 3.7416574. Now how can I prove that that's correct? Well, let me try it. Let me type it in. 3.74165, holy go to war, 74. And now I'm going to hit the x squared button and square that. And of course, what am I hoping for here? I'm hoping for 14. Well, I got pretty close to 14. These numbers, these non-exact square roots, we have a fancy name for them. Since they go on, the decimal goes on. For instance, this one, 3.7416574, actually it goes on forever with no pattern. 12865812905 with no pattern. So you really can never actually write that number down, that square root of 14. Kind of irrational, isn't it, that you can't write it down? That's why that number is actually called irrational, because the decimal never repeats, goes on, so you never can actually write it down. Hence the need for a radical sign. That's kind of radical. Let's do another one. What if we did the square root of 8? We knew what that was about equal to, but let's check it. Okay, I'm going to clear out what I have here. And to do a square root, the second and x squared, and I want the square root of 8. So I'll put an 8, and I'll hit enter. There again, it doesn't come out. Now, it just gives me a decimal approximation based on the calculator's setting here. Let's check to see if I square this number, if it comes out to 8, or even close. 2.828, no pattern. 4, 2, 7, 1. Okay, that's as far as I'll go. And I'll hit x squared and enter and see what I get. Well, it's a little bit low, isn't it? But it's as close as I can get at this point with this calculator to the square root of 8, because the square root of 8 is an irrational number. Okay? Let's come back and continue on. Okay, let's see. We also have a thing called, besides square roots, when we talk about general roots, cube roots. Okay? The cube root of 8 is the number not that if you square it, but the number that if you cube it, you get 8. Well, is that 2? I'm going to prove that it is. 2 to the third power, hence the idea of cube. Son of a gun, 2 times 2 times 2 does equal 8. So 2 is, in fact,
excellent,
the cube root of 8. You get the idea? Now, remember the square root of 64. Remember what that was? That was 8, okay? Because 8 squared equaled 64, 8 times itself, okay? Well, if you consider that, then what would the cube root of 64 be? It's not 8, because 8's the square root of 64. It must be some other number. Well, is it 4? Well, it is, actually. 4 to the third power. Very different thing, a square root than a cube root. 4 times 4 times 4 does equal 64. So you got it. The cube root of 64 is 4. Now, let's review some of the perfect cubes that would be helpful for you to know. 8 is a perfect cube. The cube root of 8 is 2, because 2 times 2 times 2, or 2 cubed, does equal 8. 27 is a perfect cube. You know what the cube root of 27 is? 3. 3 times 3 times 3, or 3 cubed, does equal 27. We just did 64. The square root of 64 is 8. The cube root of 64 is 4. Okay, we're getting a little too high, but this time the cube root of 125, you can guess, is 5. These are going to be of use to you to know, okay? It's going to be worthy of us also to know, let's look at the exponents kind of a deal here, okay? The cube root of x to the third, well, that's easy, is x. That's the number that if I multiply it by itself 3 times, x times x times x, I get x to the third. The cube root of x to the 6th, we're getting difficult here. You know what that is? We know the square root is x to the third. The cube root of this is x to the 2th, because think about it, x to the 2th times x to the 2th times x to the 2th, add exponents, gives you x to the 6th. The cube root of x to the 9th, x to the third times x to the third times x to the third does equal x to the 9th. The cube root of x to the 12th, this is a perfect one, I'm spoiling you a little bit. X to the 4th times x to the 4th times x to the 4th, adding exponents does give us x to the 12th. One more, how about the cube root of x to the 15th? X to the 5th times x to the 5th times x to the 5th does equal x to the 15th. Okay, so any multiple of 3, it looks like, is going to be a perfect cube. Any exponent that is a multiple of 3. Okay? Okay, let's consider that we may have more than one answer sometimes. Any positive square root, I'm going to prove to you, you need to know, has 2 answers. Any positive cube root has only 1 answer. How come some have 2 answers and some have only 1? That's what I want to show you. And some have none. Any negative square root has no answers. Why is that? So when you go to a test, you'll need to know, do I put 2 answers, 1 answer, or no answers? What's the deal with that? This is basic to all roots. For instance, the square root of 16, you may remember, is 4, right? Is negative 4 a viable answer as well? Well, what does it take to be the square root of 16? If you square it, you get 16. Does negative 4 squared equal 16? Negative 4 times negative 4? Son of a gun, it does equal 16. So negative 4 is also an answer. The square root of 16 is 4, and negative 4. Which is why sometimes you'll see something that looks kind of like this. The answer is 2 answers, plus, because you're too lazy to write plus 4 and minus 4, plus and minus 4. That's what that little symbol means, plus and minus 4. We'll be seeing that a lot coming up, especially this week and next week. What about this? The square root of 36, we know it's 6. Is negative 6 a viable answer? Well, if negative 6 squared equals 36, which it does, it is an answer. Okay? So the square root of 36 also has two answers, positive 6 and negative 6. And there again, for the lazies, we might see the answers to this are plus and minus 6, written like that. Okay? Now, if we consider the cube root of 8, we know the cube root of 8 is 2, because 2 times 2 times 2 equals 8. Could negative 2 work here? It's a little bit different because it's cubes. Well, let's test it out. That's the beauty of this. If you don't understand it, you can always just test it out. Does negative 2 to the third power equal 8? Well, it doesn't. It equals negative 8. That's no good. Negative 8 doesn't equal 8. Okay? So a cube root is only going to have one answer.
What is wrong with you?
Well, all odd roots are only going to have one answer. The only answer here is positive 2. What about the cube root of negative 8? Could that be negative 2? Well, in this case, actually, we know negative 2 to the third power, we just checked it out, does equal negative 8. So this does have one answer, yes, one answer,
Pay attention, son.
because positive 2 won't work in this case, but negative 2 does. So the cube root of negative 8 does equal negative 2. So you can have one negative answer. Okay? You can have everything, and if you don't remember the rules, what I do is I just test it out. Okay? What about this bad boy? The square root of negative 25. Here's where it gets really crazy. Well, is 5 valid? Well, let's test it out. 5 to the second power. What are we hoping that it equals if this works? Does 5 times 5 equal negative 25? No, it equals positive 25. They don't equal each other. So that's not going to work. The square root of negative 25 doesn't equal 5. You say, oh, I know what it is. It's negative 5. Well, it's negative 5 squared. Remember that a negative times a negative equals a positive. Positive 25. There again, these two are not equal.
Ooh, I'm dying!
We've tried both positive 5 and negative 5. Guess what? The square root of negative 25 has no real answers. You cannot take the square root of a negative number. Okay? Another rule. Okay? You could take the cube root of a negative number. We did that, but not the square root, because a negative times a negative is never going to give you that negative number. Okay? So let's review the rules we kind of just demonstrated. Any positive square root has two answers, the plus and the minus. And a cube root is going to only have one answer. It may be negative, may be positive. It depends. Okay? And you cannot take the square root of a negative number. It has no answers, because neither will work for you. Okay? That's worthy of either memorizing those rules or, as I said, just test out the theory every time you make a guess of what an answer is for a root. Okay? And now there are even higher roots than square roots and cube roots. I just want to look at them so you understand the idea of testing something out. Okay, for instance, the fifth root of 32. Woof, this is a tough one. Well, whatever it is, it's the number that if I multiply it times itself 5 times, times itself, not times 5, times itself 5 times, I get 32. What would that be? Well, I'm going to take a wild guess and hope that it's 2. Let's see, 2 times 2 times 2 times 2 times 2, 5 times, does equal 32. You understand what I mean then when I say the fifth root of 32 is 2. Maybe one other one. We know the square root of 81. We already knew that that's 9. Actually, it's plus 9 and minus 9, okay, because 9 squared does equal 81. However, what's the fourth root of 81? What number times itself 4 times, not times 4, equals 81? Well, it's 3. 3 times 3 times 3 times 3, son of a gun, does equal 81. So the fourth root of 81 is 3. So there are higher roots.
Genius!
Okay?
That's what it is.
Thank you.
Sheer genius! you?
But I don't want to dwell on this. I just wanted you to get the idea, the theory of what we're doing here. Okay? Okay, now we're going to start simplifying these babies. Let's see what we'll talk about simplifying. Now, most of our problems for this whole chapter and the next one are going to be spent simplifying radicals. Okay? What's the deal? Well, before we get to simplifying radicals, let's review a little bit of what's critical to simplifying radicals, and that basically what we're doing is pulling out the perfect ones. Okay? Now, you've already forgotten a perfect one, haven't you? Remember that 4 is a perfect square root. I told you that you'd need to know this because the square root of 4 is 2. Quickly, the square root of 9, what was that? 3. Square root of 16, these are the perfect ones. The square root of 25, the square root of 36. Don't cheat and look at the bottom and find the pattern. Square root of 49, these are going to be all the ones that come out even. Okay, and most don't come out even. Square root of 64. And they get higher than that, but that'll do. I won't give you any harder ones than that usually on a test. And it's going to work. You're going to need to know the perfect ones for variables as well. Okay? And basically the deal with that was any even variable is going to be a perfect square root. For instance, 2, the square root of x to the second is x to the 1th. Square root of x to the 4th was x to the 2th. The square root of x to the 6th, that was the first crazy one, was x to the 3rd. Because remember why? X to the 3rd times x to the 3rd, and we add exponents gives us x to the 6th, so it's a valid square root. That's why any even one, basically we're going to divide it by 2 and get the square root. The square root of x to the 10th is going to be x to the 5th, right? X to the 12th, x to the 6th, okay? That kind of a deal. So any even variable exponent is going to give you a perfect square root. Okay, just wanted to quickly review that because that's going to be critical in upcoming times. Okay, another thing that would behoove us to remember is some fancy words, and that's the difference between factors and multiples. Remember that if you take 12, factors are the numbers that go into 12, like 2 goes into 12 evenly, 3 and 4. These numbers are called the factors of 12, okay, as opposed to numbers that 12 goes into, 24, 36. These are called multiples, okay? Numbers that go into 50, 2. Now 3 doesn't go in evenly, so he's not included there. 5 goes in evenly, okay? 10 goes in evenly, so these are factors. Numbers that 50 goes into, or that a number goes into again, are multiples. Okay, it's going to behoove us to know those words. Okay. Okay, now remember, we're going to do simplifying fractions. Simplifying factors. Okay? And what we're going to be doing is taking out the perfect squares, that's why you needed to know them. And once you had taken out the perfect squares, whatever was left, the garbage, is what we're going to break up. Okay? That's why you needed to know the perfect squares. Let's take a look at some simplifying radicals problems. How will you know when something is already done or not done? A radical or a root is in simplest form when the thing inside, the radicand, that's a fancy word, doesn't have any factors that are perfect squares. Remember what a factor is. Okay, so when the radicand, the thing inside, doesn't have anything that goes into it that is a perfect square, you're simplified. Okay? Now, the square root of 24, is that simplified? Does it have any factors that are amongst your perfect square roots? Well, there is a perfect square root of 4 that goes into that, so that one's not simplified. Okay? What about, because it has a perfect square root, 4 goes into it. Okay? 18, are there any of the perfect squares go into that? Well, it isn't in simplest form because what is the troublemaker that could possibly go into 18 that is a perfect square? Can you think about it? 9. Okay, so this isn't in simplest form either. We're going to have work to do here. Simplest form? Actually, it is, because I can't think of any factor of 10, you say 2 and 5, but neither of those is a perfect square. So this is already in simplest form. Okay? x to the third. Now we know the factors, things that go into x to the third. Is any of our perfect squares a factor of x to the third? Well, this one is not in simplest form because something goes into it that we know the square root of. X to the second. Okay, so he can be broken up is my point. Okay? How are we going to break this up? What do you mean break it up? Well, consider our new product rule of radicals. Product meaning multiply. Did you know that the square root of a times b, you can break that into the square root of a times the square root of b? For instance, the square root of 36, 36 being 9 times 4, is the same, the square root of 36 is the same as the square root of 9 times the square root of 4. Square root of 36 we know as 6. Isn't the square root of 9 3? And the square root of 4 2. And 6 does equal 3 times 2. Okay? This is just a demonstration of this rule.
That's what it is. Sheer genius.
Now you might say big deal, but this product rule, the square root of two numbers multiplied, is the multiplication or product of the two square roots, is going to be of great use to us in simplifying these radicals. For instance, let's simplify the square root of 18. We're going to break him into, or factor him into, I should say, the perfect square root that you know goes into it, the largest perfect. We want to take out as much goodness as possible, the perfect squares, and once you've taken out the perfect squares, whatever's left will be the garbage. Okay, we're going to use a product rule to break this into the perfect square of, it's going to behoove you to know, 9, which goes into 18, and once I divide 9 into 18, what's left over is 2. Okay, now why did I break it that way? Well, the square root of 9, I can take the square root. It's 3. The square root of 2, I can't do anything with, so I don't. And that is the square root of 18 simplified. It's written 3 radical 2. You've taken out as much exactness, if you would, as possible. But it's going to be the same idea every time you try to simplify it. We're going to break it into good and evil. The square root of 75, we want to factor it into good and evil. The perfect square roots and the garbage left over. What's a perfect square root that goes into 75? I hope you memorized your list. That leaves us with 3. Now the square root of 25 is 5. And the square root of 3, the reason it's left over is because there's nothing I can do with it. And there's your simplified radical 75, 5 square root of 3. You say, that's the same thing you did last time. We're going to be doing the same thing every time, breaking them into good and evil. Ooh, this is a tough one. Square root of 128. Do you know any good square roots that go into that? Well, it would behoove you to try to factor things in that are good, and then we don't look for the bad, we look for the good, and then whatever's left over is the bad. Actually, the good that goes into 128, now a 4 would go into 128, but there's an even bigger good. We want to take out as much goodness as we can, and that's 64. Leaving me with 128 divided by 64 is 2. The square root of 64 is 8. And I just bring down my garbage.
Genius! That's what it is.
And that's a
Sheer
simplified
genius.
radical. What if we do this with variables? Same deal. Let's break it into good and evil. Now what's the largest good square root that goes into x to the 7th? You've got to know your variable square roots. X to the 6th. Leaving me with, does x to the 6th go into x to the 7th? Remember what happens when we divide exponents, we subtract. Leaving me with x, or x to the 1th. Okay? And the square root of x to the 6th is, that's why we reviewed it, x to the 3rd, and the garbage we just can't do anything with. And you have now simplified that radical. It's not so bad, it's the same stuff. You just have to know, or at least have written down, your perfect square roots. Let's look at this one. I want to break it into good and evil. The biggest good square root. The biggest, remember that was the even ones. What's the largest even root that goes into this, or even exponent? A to the 20th. And that'll leave me with A to the 1th, or A. The square root of A to the 20th is A to the 10th. Not so bad. And my garbage. This is easy. Okay, you're in the big leagues now. Let's do a mix of both.
Ooh, I'm dying.
It's not that hard, Francis. Let's try it. Break it, the same principle, break it into good and evil. Sometimes it helps if you hum. Square root of 50, I'm going to break into 25 and leftovers of 2. Okay? Now let's take it one thing at a time. X to the 3rd I'll break into X to the 2th, leaving me with X to the 1th. Take it one at a time. A to the 6th. Now sometimes they're all good. The whole poopsie's good, and there isn't any bad. Okay? And other times, as in the B, they're all bad. There isn't any good. So it just goes in the bad pile. Okay? Now that I've broken them up, I take my perfect square roots, the square root of 25, x to the 2th, a to the 6th, and take it. That's why I set it up to do that. And I just bring the garbage down. Okay? You demand. Okay? Now there's a little bit a twist in this one. We do have a number out there too. We're going to break up the radical. We're not breaking up the number. I'm breaking up square root of 125 into, forget the 2 for just a second, 25, perfect square root, and what's left over? 5. Okay? Oh, now bring your 2 down. Okay? Now, the square root of 25 is 5. And I bring down my square root of 5. Don't forget the 2. And now 2, since 5 is now a number, 2 will talk to him. And they can now get together and become a 10. Okay? So sometimes if you have a number out there, you might have to end up multiplying it at the end. But that's as hard as it would get. Okay? Now if we want to add and subtract radicals, they have to be alike. And they should be simplified. So basically what we're looking at here is just more of the same. Let's take a look. For instance, 5 times the square root of 3 plus 2 times the square root of 3. These are alike. We have that like term, the square root of 3, so we can just put them together and we get 5 plus 2 times the square root of 3, or 7 square root of 3. We're making it harder than it needs to be. Just add like radicals. Okay? How about this one? Well, these ones aren't alike. You do not have that one term to put them together, so guess what? If you don't have that, they're unlike, you can't do any more, they're done. It's like adding 2x and 3y. Okay? Now let's look at this. We're looking for like radicals. I see square root of 3's, and I have 5 of them, and I have minus how many? Minus 1 of them. When you don't have a number, it means 1. Okay? So the 5 minus the 1 will be 4 radical 3's. It's much like variables, isn't it? Okay, the square root of 2's, I got 3 of them, and I got plus 4 of them, so I got 7 of them. Okay, not so bad. And then nobody likes 3 square root of 7. No, nothing alike with him, so we just bring him down. That could happen. That wasn't so bad, was it? Just adding like radicals. How about this one? Well, now, these aren't in simplest terms. There's going to be an extra step here that we're experts at, and that is simplifying them first. Let's see, let's take it one at a time. The square root of 18, I'm going to break into good and evil. The good is a perfect square root of 9, and that leaves me with 2. So I've simplified square root of 18 to 3 radical 2. Okay, now let's get the next one. Let's break 2 radical 125. Let's break up that radical into good and evil. The good, 25, and the bad, in this case, 5. Now, radicals don't talk to numbers, okay? I want to use the word racist, okay? Radicals don't talk to numbers, numbers don't talk to radicals, okay? So, that 2 cannot talk to that 25. But what's about to happen here is that square root of 25 is about to become a 5. Oh, well now, why didn't you say so, Dorothy? Come, we'll talk to you now. 2 loves 5. Why? Because it's not a radical anymore. It's a number. Now they'll talk. And 2 times 5 is, of course, 10. Okay? Remember that? Okay, let's bring him down. He's already simplified. Nothing goes into him. So we'll just keep bringing him down. Now all I have left, everything's simplified. I just have to add like radicals. Now these 2 are like. I have 3 of them, and I have what? 1 of them. I don't see the 1, but it's there. So I end up with 4 radical 2's. And the 10 radical 5 has nobody to add with, so I just bring him down. Not so bad. Just a whole lot of simplification, isn't it? Okay? Here's a bad Johnson. Let's look at this one. Take it one thing at a time. I like to when I need to, okay? Let's break him into good and evil. Let's see, the 32 is 16, and the scum would be 2. X to the 3rd, I'll break into x to the 2th and x, okay? Taking the perfect square root, 16x to the 2th, I'll get 4x, and I'm left with the garbage, 2x. So this guy's simplified. Now, can we do anything with the middle term here? Well, I'm going to break up that radical 8x into good and garbage. Well, let's see. The number will be 4, left with 2x, okay? Well, let's see. That was as much goodness as I can take out. 4x won't talk to that radical 4 because it's a radical, but in a second, we know what radical 4 is going to become. He's going to become a 2. Well, now 4x loves him, and they'll talk and get together, and we'll get an 8x, okay? The 3rd term is already simplified. It's not always that the 3rd term is simplified, but in this case, there's nothing I can break 2x into, so let's just bring him on down. Okay, and all we have left to do is put together like terms. Well, let's see, I have 4x, 8x, and minus 1x. You see that 1 there. And what does that add up to? 4 and 8, 12, minus 1. We get 11x, square root of 2x. That is a tough problem, and we did it. Well, it's time to review. Okay, that's enough for today. Let's review what we did. As far as radicals and roots, any basic positive square root has 2 answers. The positive one and the negative one. For instance, the square root of 16 has a plus 4 and a minus 4. Okay? Any cube root is only going to have 1 answer. For instance, the cube root of negative 8 is only negative 2. The cube root of positive 8 is only positive 2. And you could just test these out. You don't have to remember these rules. And you cannot take the square root of any negative number. Trying to take the square root, for instance, of negative 9, 3 won't work, negative 3 won't work. Okay? So those are the basic rules. Remember that you can take square roots with a calculator. You need to know a little bit of the trick. That, of course, the on button. This x squared button can be turned from an x squared button to a square root button by hitting the second, the button that actually says second, and then hitting the x squared, and it becomes the square root button. So typical steps to taking a square root would be to hit the second button, to hit the x squared, that changes it into a square root button. Type your number, whatever it may be, and then you have to hit enter to tell it that you're done typing the number. Okay? And it'll display for you the appropriate square root. Okay? Well, let's see. What about that? We reviewed a little bit about simplifying a radical in simplest form. Okay? When is it in simplest form? When the number inside the radical, the radicand, doesn't have any number that goes into it, a factor, that is a perfect square. Remember that it would behoove you to remember or familiarize yourself with those perfect squares. Okay? But you'll need to recognize when they're factors of the radicand. Okay? For instance, square root of 24 wasn't simplified because there was a number that went into 24 that was a perfect square, in that case 4. Okay? Then, the ones that weren't simplified, we simplified by breaking them into, or factoring them into the good, the perfect square roots, and whatever was left over, the garbage. In this case, breaking up square root of 18, I'll break it into the perfect square root, 9, and what that leaves me with, a 2. Okay, now the perfect square root 9 is a perfect square root because I know what it is. It's 3. And then I bring down the garbage, and it is garbage because I can't do anything with it. And that's how you simplify that radical. Okay? When we involve variables, at least with square roots, we're looking for the largest even square root when we're looking for the good ones. We'll break him once again into good and whatever's left over. The largest perfect square root here, in this case, is going to be x to the 6th, because I know the square root of x to the 6th. And that leaves me with, when I divide x to the 6th into the x to the 7th and subtract exponents, leaves me with x to the 1th, or x. Taking my perfect square root, I get x to the 3rd, and bring down my garbage. This radical is simplified. Sometimes we have to do a mixture of everything. And it's not hard as long as you take one part of it at a time. For instance, in this case, we broke the large radical into 2, started with 50, broke him into a perfect square of 25, leaving me with 2. I got the x to the 3rd, breaking it into perfect square of x to the 2th, remember the largest even one, and that leaves me with x to the 1th. A to the 6th is all good. Sometimes they're all good, and sometimes they're all bad. For instance, the b just goes over in the garbage pail. Okay, now we don't throw it out actually, but we can't do anything with it. Now, the perfect square roots, we can take that square root. The square root of 25, x to the 2th, a to the 6th is 5x, a to the 3rd. And then I just bring the rest down because there's nothing I can do with it. And that's about as hard as you're going to get. We remember the idea of adding like radicals, radicals that have the same radicand. These two have radical 3. 5 radical 3 minus 1 radical 3 gave me a 4 radical 3. The radical 2's can get together, 3 of them and 4 of them, give me 7 of them. And I don't have anybody in this problem that is a radical 7, so he'll just sit by himself. Now, we don't start adding like radicals here until we simplify, and then we find out who is alike. You may find something that's alike that you didn't know was alike at the beginning of the problem. Let's break up these problems. Let's break it into 3 separate problems. The square root of 18, I'll break into 9 and 2. It becomes 3 radical 2. This next one, kind of a mixed number, break square root of 125 into 25, and what's left over, the 5. Now that square root of 25 we know becomes a 5, and now remember the 2 will talk to him and they'll get together. And let's bring down the radical 2, which is already simplified. There's nothing that goes into 2 that is a perfect square. So we just bring it down, and now, and only now, we can add like terms. I got 3 of them, and I got 1 radical 2. I got 3 radical 2. That makes 4 radical 2. And the radical 5 term, nobody's alike with him, so he just comes down. That was tough, huh? Nah. Well, I guess it's time to go.
I better get out of here while the getting's good.
Remember that if I went too fast, if you want to play back these programs at your own speed, that you can go to our homepage. I hope you've been doing this at www.montgomerycollege.edu/algebra.
That's all, folks.
Of course, all of this is of no use if you don't do your homework. And you'll turn that into me, so make sure that you do your homework, because if you don't...
You better say your prayers, you flea-bitten varmint. I'm gonna blow you to smithereens.
I'll see you next week. Have a good one.